In today's lecture, we will focus on crucial aspect of operating systems, process synchronization. We will examine the differences between independent and cooperating processes and understand why cooperation is necessary in certain scenarios. Additionally, we will delve into the critical section problem, which highlights the need for synchronization mechanisms in cooperating processes. Lastly, we finish today's lecture with software solutions for critical section problem. Yeah, and also their drawbacks. Okay, let's start. A process within a system may be independent or cooperating. Independent processes are unaffected by the execution of other processes. They operate in isolation and they have no interaction or dependency on other processes, okay? And also, each process has its own resources and executes independently. On the other hand, cooperating processes interact and collaborate with each other. They can affect or be affected by the execution of other processes. Cooperation involves sharing data, resources, or coordinating activities. Okay, then cooperating processes may have several advantages, including information sharing, computational speed up, modularity, and convenience. So in information sharing, advantages of the cooperating process, they may need to exchange data or information to complete a task, and sharing information allows processes to communicate and make decisions based on shared knowledge. And in the computation speed up advantage, we can divide the complex task among cooperating processes, and with that way, computation speed can be increased. Each process can work on a separate part of the task simultaneously. Overall, it reduces the execution time. On the other hand, the cooperation also allow for the decomposition of a complex problem into smaller, manageable modules. So we can say that it also enhances modularity. So each module can be assigned to a separate process and making the system more modular and easier to develop and maintain. And lastly, it enhances the convenience, the user convenience. Cooperating processes can provide convenience and flexibility to users, okay? For example, in a client-server architecture, the server process handles resource-intensive tasks, while client process provide a user-friendly interface. Yeah. So in conclusion, we can say that cooperating process play an important role in systems where interaction, data sharing, and collaboration are required. And by cooperating, process can share information, speed up computation, achieve modularity, and provide convenience to users. If we understood the benefits and reasons for cooperating process, we may look at communication ways of processes. So, in the context of process interaction, there are two common approaches, okay? First one, passing messages through the kernel and sharing a region of physical memory. So let's explore the differences between these two methods. In passing messages through the kernel, in this approach, processes communicate with each other by sending messages through the operating system kernel, okay? So when a process wants to send a message to another process, we have process A and process B here, okay? So when a process A wants to send a message to process B, it invokes system calls to pass the message, okay? Remember that system calls are provided by the kernel, and the kernel behaves like an intermediary, which facilitates the communication between the sender and receiver processes. So it helps the communication of process A and process B. This method actually offers a level of abstraction and isolation between processes, as they do not have direct access to each other's memory. However, the involvement of kernel and system calls, as you guessed, it can introduce some overhead and potentially impact real-time performance. In the case of sharing a region of physical memory, in this approach, processes interact by directly sharing a region of physical memory. Okay, the shared memory area is explicitly allocated and accessible to multiple processes. Processes can read from and write to the shared memory area, which allows for fast communication. For example, in this figure, process A can write to shared area and process B can read it from that shared area, okay? Since they have direct access to the shared memory, communication can be performed without involving the kernel, okay, which eventually leads to lower overhead and potentially better real-time performance. However, sharing memory introduces the need for synchronization mechanisms to ensure proper coordination and also prevent data conflicts between processes. Yes. In summary, both methods enable real-time process interaction, but they differ in terms of communication channels and overhead. Okay, so passing messages through the kernel provides abstraction and isolation, but may introduce some uh, overhead due to system calls. Sharing an area of physical memory offers direct and efficient communication, but it requires synchronization mechanisms, yeah, to handle these potential data conflicts.